So as I explained, the simulated parameters approach makes strong assumptions about the distribution of the estimated parameters. And we can sample from that distribution because we have a strong assumption of its shape. For example, a multivariate normal distribution. And that makes it a parametric method. Bootstrapping is a non-parametric method in the sense that it does not make particular assumptions about the distribution of our estimated parameters. And that makes it more flexible and applicable in more circumstances, but it also makes it computationally much more expensive. So here are the steps of a bootstrap procedure. You take a random sample of the original sample that you have, of the original data set. And that sample has to have the same size, so we have the exact same number of observations. But because we sample with replacement, that means that every observation we have sampled is put back in the data so that it can be included in the next sample point. The result is that we get a data set that is the same size as the original data set, but many observations will have been included 2, 3, or 4 times, and many observations will have been left out. So the exact sample looks different because of duplication and deletion of observations, even though it is the same size. And we do that m times, and each of those times we re-estimate the model that we had estimated, and we look at the coefficients and we calculate maybe a predicted value. And then at the end we can look at the distribution of the predicted values. And so here we are never making the assumption about the normal distribution or other distribution of the coefficients. And so we have we have weaker assumptions there. But every sample we need to re-estimate the model. Where for simulated parameters we only needed to estimate the model once. It has been shown that when you calculate a statistic over these bootstrap samples, so each bootstrap sample you calculate the same statistic and then you look at the distribution of that statistic across bootstrap samples, that this will have the same distribution as the sampling distribution of that statistic for the original sample. Yeah, so we get an idea of the sampling distribution, which is what we normally use in the frequentist framework to assess uncertainty. So bootstrapping is very much a frequentist approach to uncertainty, because we're trying to approximate the sampling distribution of the statistic by looking at the distribution of that statistic across bootstrap samples. And it has been shown that these estimates of uncertainty might be biased but are inconsistent. So as the sample size increases, or as the number of bootstrap samples increases, it converges to correct estimates of uncertainty. So here's a simple example where we calculated the mean age of a particular sample, and we take bootstrap samples each iteration of all those ages, and each time recalculate the mean. And then we look, by looking at the quantiles, we can look at a 95% confidence interval of this estimated mean